So our change in gravitational potential energy was mg delta y. What is the work done by gravity? What's the magnitude of the gravitational force? mg. A distance would be delta y. In what direction is gravity? Down. A positive delta y is up. If I move something up, does gravity do positive or negative work? Work done by a spring, we worked out the other day. We derived it in two different ways, using a graphical method and also doing an integral. We got that was 1/2 k x final squared minus x naught squared. Change in spring potential energy, 1/2 k x final squared minus x naught squared. Do we see a pattern? The work done by a conservative force is equal to negative a change in potential energy. That make sense? Okay. We also know, what's our definition of work? Calculus definition of work? Right. So that means that negative, if our force is a conservative force, negative change in potential energy equals integral of f dot dr. And then by the fundamental theorem of calculus, which the fundamental theorem of calculus says that if there's an integral relationship, then the reverse also applies. That, like, you can take a derivative, yeah, and go the opposite way. So if negative change in potential energy is the integral of force, that means that a conservative force can be found by taking a derivative of the potential energy function. And then there's this negative, so negative. So force, a conservative force, is the derivative of its potential energy function with respect to whatever kind of displacement is relevant. So for spring, what's the formula for force, or for potential energy? That's the change in potential energy. So just the potential energy is 1/2 kx squared. So if we want to find spring force, what do? Well, we derive that and then make it negative, because negative. So what's spring force? Minus kx. Whoa! Spring force. Gravitational force then is equal to minus d by dy of mgy, which is what? Minus mg. Gravitational force of mg in the negative y direction. When we wrote this equation, we assumed that positive y direction was upward. So, whoa! So given this derivative relationship, if we have a graph of potential energy versus displacement, what would slope represent? Almost. Right. The opposite of force. So if the slope is positive, the force is negative. Slope is negative, force is positive, etc. Try to be tricky. What would a graph of spring, what kind of shape is a graph of spring potential energy versus displacement? Is what? It's a parabola, right? Pretend that's a parabola and not pointing at the bottom. Right, so if x is greater than 0, what is the slope, what is the derivative of this? It's going to be positive, which means the force is negative. That means F is in the minus x direction. For x is less than 0, the slope of the graph is negative, which means force is in the positive x direction. And at x equals 0, force is 0. Yep. What does equilibrium mean? Equilibrium means net force is 0. Yeah. So if you're given a potential energy curve, you can find equilibrium points by finding where the derivative of the graph is 0, the instantaneous, the slope of a tangent line is 0. Yeah, calculus. How about that? What do you mean suddenly? We took a derivative like 2 minutes ago. There are 3 types of equilibrium. There is stable equilibrium. It's when all your horses are standing still. Ha ha ha. A stable is a place where you keep horses. All right. If there's stable equilibrium, what do you think another kind is?
Unstable.
Unstable equilibrium. And there's one more that you might not be able to guess, but it's called neutral equilibrium. Okay. And the question you're asking, as you consider what kind of equilibrium this is if you displace your particle a tiny bit, what does it do? Okay, if you displace it a little bit in either direction, and its tendency, there's a force that pushes it back toward the equilibrium position, then that equilibrium is considered to be stable, because it tends to stay there.
So it's like when you're pushing against the wall.
What? No. Not when you're pushing against a wall. But like with a spring, like you got your mass sitting there at equilibrium, you push it one way, well, it'll tend to push back the other direction. If you push it to the left, it'll push back to the spring will push it back to the right. So that, no, is not stable because it doesn't tend to go back. An example of this is if I sit my water bottle like this. You know, I push it a little bit, it goes back. This is rotational, not translational, but you get the idea. If I managed to balance my water bottle like this, and I pushed it a little bit, what would it do? It would fall. So that is unstable equilibrium. So stable, I should say this, a small displacement results in a force pointing back toward equilibrium. So what would you guess unstable would be?
Not pointing.
The small displacement results in a force pointing away from equilibrium. And then neutral equilibrium, a small displacement results in 0 force. An example of neutral equilibrium would be if I had my water bottle like this on a frictionless surface. If I push a little bit, it would just keep rolling. You know, it wouldn't go back, and it wouldn't accelerate away. It would just go. Yeah. I forgot when I was making the note packet. I had some thought for what that blank was going to be, but I don't remember what it was. I think it had something to do with explaining the 3 different types of equilibrium. So we're good.